Deep-sea fish and invertebrates can live several kilometers beneath the surface. They are not diving. Their bodies remain at depth, and they obtain oxygen directly from the surrounding water. Air-breathing animals face a different challenge. Every dive begins with a limited oxygen supply. Whatever oxygen they carry must keep their brain, heart, and muscles functioning until they return to the surface. Depth also brings pressure. For approximately every 10 meters an animal descends, the pressure increases by another atmosphere. At 100 meters, the total pressure is around 11 atmospheres. At 1,000 meters, it is approximately 101. And at 3 kilometers below the surface, an animal experiences roughly 300 times the atmospheric pressure found above the ocean. Most of the body is made from water-rich tissue and is not easily compressed. The greatest problem comes from spaces containing air, particularly the lungs. A human attempting to descend to extreme depths would risk lung injury, nitrogen narcosis, decompression sickness, and eventually a complete loss of consciousness as oxygen ran out. That does not mean humans are poor divers. Elite freedivers can descend well beyond 100 meters on a single breath. And with scuba equipment or saturation diving systems, humans can go much deeper. But our deepest dives depend heavily on training, planning, and technology. Deep diving animals carry the solution inside their bodies. They must store enough oxygen, tolerate the pressure, manage their circulation, and return to the surface without equipment or outside help. Even birds can reach surprising depths. Emperor penguins usually hunt between around 150 and 250 meters below the Antarctic surface, but the deepest recorded dive reached 565 meters. At that depth, the pressure is more than 50 times greater than at the surface. Although penguins breathe air, their bodies are designed for extended underwater movement. Dense bones reduce buoyancy, powerful chest muscles drive their flippers, and their streamlined bodies minimize resistance. Before a dive, an emperor penguin can increase the oxygen stored in its blood and muscles. Once underwater, its heart rate can slow dramatically. Blood flow is reduced to less immediately important tissues, preserving oxygen for the brain, heart, and other vital organs. This allows the penguin to remain active beneath the ice while using its limited supply carefully. Marine reptiles can descend even farther. The leatherback is the largest living sea turtle and one of the deepest diving reptiles. A recorded leatherback dive reached approximately 1,344 meters. Leatherbacks normally feed on jellyfish and other soft-bodied animals. Their prey can move vertically through the ocean over the course of a day. Following them may require the turtle to travel far below the sunlit surface. Unlike other sea turtles, a leatherback does not have a rigid, solid shell. Its back is covered by a flexible layer of leathery skin supported by smaller bones. This flexible construction may tolerate changing pressure more effectively than a completely rigid air-filled structure. Leatherbacks can also slow their heart rate and redirect blood flow during prolonged dives. Their large bodies retain heat, allowing them to remain active in cold water that would rapidly cool a smaller reptile. But mammals dominate the greatest recorded depths. Southern elephant seals routinely dive hundreds of meters while searching for fish and squid. They spend most of their time at sea moving through a continuous cycle of descent, hunting, and return. The deepest recorded southern elephant seal dive reached approximately 2,388 meters. Elephant seals carry unusually large oxygen reserves in their blood and muscles. Their blood contains high concentrations of hemoglobin, while their muscles contain large quantities of myoglobin, a protein that stores oxygen directly within muscle tissue. This is important because the lungs are not necessarily the safest place to carry oxygen at extreme depth. As a marine mammal descends, increasing pressure compresses its lungs. Eventually, the tiny air sacs where gas normally enters the blood begin to collapse. Air is pushed into stronger central airways that can tolerate compression more safely. Lung collapse sounds dangerous, but for a deep diving mammal, it can be protective. Once the gas exchanging surfaces have closed, less nitrogen can move from the lungs into the bloodstream. This reduces the animal's exposure to the high dissolved nitrogen levels that can cause decompression sickness during ascent. The compressed lungs also make the animal less buoyant. Some seals and whales can stop swimming during part of the descent and glide downwards, conserving both energy and oxygen. Sperm whales are among the most familiar deep-diving mammals. Most of their foraging dives are far shallower than their maximum capabilities, commonly reaching around 600 meters and lasting approximately 45 minutes. But recorded sperm whale dives have approached 3 kilometers. They descend in search of squid and fish, using powerful echolocation clicks because sunlight cannot penetrate to their hunting grounds. The animal must not only reach the prey, but locate it, pursue it, capture it, and return while relying entirely on stored oxygen. However, the deepest authenticated mammalian dive belongs to a much less familiar animal. Cuvier's beaked whales live in deep oceanic waters and spend relatively little time visible at the surface. Satellite-linked tags have recorded them routinely diving beyond 1,000 meters, often remaining submerged for approximately an hour. One recorded dive reached 2,992 meters. At that depth, the whale was exposed to pressure approaching 300 atmospheres. Another Cuvier's beaked whale remained underwater for 3 hours and 42 minutes without returning to breathe. The longest and deepest records came from different dives, and these exceptional events do not represent the animal's normal behavior, but they reveal how far their physiology can be pushed. Exactly how they remain submerged for so long is still not completely understood. Like other deep-diving mammals, they conserve oxygen by slowing the heart and restricting circulation to selected tissues. Their muscles store large amounts of oxygen, and their flexible chest structures allow the lungs to compress. They also move efficiently. Rather than continuously powering themselves downwards, beaked whales can use their streamlined bodies and changing buoyancy to glide through sections of the descent and ascent. The final limit is not determined by pressure alone. An animal must carry enough oxygen to descend, hunt, and return. It must tolerate rising carbon dioxide levels, protect its organs when blood flow is restricted, prevent excessive nitrogen absorption, and avoid damaging its lungs as they collapse and reinflate. A record dive, therefore, represents a balance between depth and time. Descending farther takes longer. Hunting consumes oxygen. The deepest dive ever recorded is also not necessarily the deepest dive that has occurred. The current records tell us what scientists have managed to measure, rather than the absolute physiological limit of every species. But the measurements already extend remarkably far. An emperor penguin can reach more than 0.5 kilometre, a leatherback turtle can pass 1 kilometre, an elephant seal can descend beyond 2 kilometres, and a Cuvier's beaked whale can approach 3 kilometres below the surface before turning around and swimming back towards the air. For these animals, the deep ocean is not a place they merely survive. It is somewhere they repeatedly choose to hunt,